Hello and welcome to this presentation on audio. If you can see this diagram here, we can think of audio as a wave. This is just a sine or cosine wave, but it can be representative of simple audio. If you can imagine the surface of a drum or a guitar string, when you strike the drum or pluck the guitar string, those objects vibrate back and forth, and you can imagine this would be one extension of it, and then it returns and goes back down, and then returns and goes up and goes back down. And this vibration causes a vibration in the air molecules, and that vibration of air gets transferred to the bones in your ear, and we perceive that as sound. So this simple sine wave is a fairly good, easy representation of a very simple sound. And there's two key properties that we want to look at. One is the amplitude, and that is how far does the wave extend above and below its baseline or resting point. And that amplitude is related to the intensity or how loud the sound is. Another property that's related to the inverse of the period, and that is frequency. How many complete waves do we get in a time period? So how many waves do we get per second? And that frequency is measured in hertz, so it's waves per second or hertz. And that frequency relates to the pitch of the sound. How high or low pitch is the sound? In our digital environment, the sound is sampled at regular intervals. So these blue dots that you see here may not be obvious to you, but they are actually equally spaced along the x-axis. They're not equally spaced along the curve, but they are equally spaced along the x-axis. And so these might be representative of samples of the audio taken at regular intervals in time. And that's how sound is represented typically in our digital world. Here's a representation of maybe a more complex sound, and when it is sampled or digitized, it has certain properties that we may be interested in. One is the so-called sample size. So every one of these sound samples is stored in a variable, and how many bits or bytes is that variable going to take up? The more bits or bytes that we use for the sample size, the greater the resolution, the greater detail we can store for the sound. However, there's a trade-off in that the larger the sample size, the more data and memory this is going to take up. It's very common to have sample sizes of 16 or 32 bits, sometimes even smaller. Another property of our sampled data is the sample rate. And this is the frequency of the samples, not the frequency of the sound, but the frequency of the samples. So how many of these blue dots do we have per second, or how many samples do we have per second? So the sample rate, the number of blue dots we have per unit of time, is different than the frequency of the sound, the number of waves we have per unit of time. And again, the higher the sample rate, the more accurately we can represent the sound. But again, the higher the sample rate, the more samples we'll have in our file, and the more storage and memory it'll take up. Another property is the number of channels. Mono and stereo are two options, and then of course today we have even greater number of options with surround sound and so on. Here we have a stereo sound, and so there's two separate channels of audio. couple of other properties are the length or duration. So how long is the sample in seconds? And if you take the sample size in bytes and multiply it by the sample rate and multiply it by the number of channels and multiply it by the length in seconds, you'll get the approximate number of bytes that an uncompressed wave data or sample data would take up. As an alternative, music can be stored in a MIDI format. And a MIDI format is very different in that it does not store sampled sound. Instead, it stores instructions on how to play the sound. So if any of you are musicians, the MIDI format would store what note to play, how long to play it, what's the timing of the note, and how does the note increase and decrease in volume, so and what instrument to play the note on as well. So MIDI is more like sheet music that a musician would look at, where it has instructions on how to play it. So because MIDI does not have many sound samples, MIDI files are generally small. The downside of MIDI files is that depending on what hardware you play it back on, it may sound very synthetic. So if the MIDI file calls for playing this piece of music back on a cello and a French horn, and your hardware is not able to recreate those type of instruments accurately, you may end up with a very synthetic sounding piece of music. Another potential problem with MIDI is, how would you play somebody speaking or sound effects like a thunder or a crash or an explosion? That's a difficult thing to recreate on an instrument with music. So MIDI's somewhat challenged by speech and sound effects. So typically we have some type of digital data similar to wave data. We're going to look at a different API or software development kit called withFMOD, and this is a free download. You do have to register, but it's a free download. So if we go to the withFMOD website, you can see that you need to log in or log in to download it. And when you do, you can download the withFMOD, not the Studio tool, but the Studio API is what you should download. And you'll probably want the Windows 10 version, the Windows version, or maybe the Windows 10 version. And when you install it, mine got installed to the Program Files x86, withFMOD, API, and we're going to use the low-level API. And these are some of the folders that we'll be looking at. The include folder and the library folder, we'll take a look at those in a minute. Additionally, you'll see that there are documentation resources for the API, and they include examples as well as a low-level API reference. And so you can see they have a system, they have channels, they have sound, and we'll take a look at just a few of the basic capabilities today. But this is a nice, fairly simple, fairly easy to use API for recreating sound. You do have to register and give them an email address, set up a password, but other than that, it's free to use. And there are other APIs that you can use. There's a OpenAL, Open Audio Library, the old DirectX had a direct sound API, and there's a variety of others that you could use. But I find this to be fairly simple and easy to use. So let's take a look at the paths again. As I said, when I installed it, it ended up in my program files x86, FMOD sound system, Studio API for Windows API, and there's different APIs. We're using the low-level API, and here's the include folder, and this is the header file that we'll be using, and this is the library file, and depending on whether you have 32-bit or 64-bit Visual Studio, you'll use one of these two library files. And then there's also a DLL that we will have to get access to when we go to run this. Again, here's the documentation. They have examples, they have reference on the low-level API. Very good documentation on how to use this. And again, we're just going to cover really just a few commands to create the sound system, load up a sound, and play it. It's really that simple. So here's some of the code changes that we'll look at. The first is we'll include the fmod header file. So I put it in the application class. So I included the fmod header file, and then I said using namespace fmod. And then we created a few variables, a few pointer variables. One is for the fmod sound system, another is for a particular channel, and then a couple others for two different sound effects that we'll load up. Here's the initialization, pretty straightforward. We create this sound system, we initialize it, we load up a couple of sounds. So we load up P sound, and which is, and again I put these in our media folder. So I grabbed a couple of Windows sounds from the Windows System Media folder, the chimes.wave and the stop.wave that you may recognize. So we load those up into the two different sound variables, and then we play them. So this code is from the picking demo. And what I did was in the picking function, the picking test function, if the ray hit an object, I set the, if the ray hit an object, I set the sound so that it's not looping and play it. If we finish the loop through all the billboards or all the triangles in the billboard and we did not get a hit, so not hit, I took the second sound and turned the looping off and played the second sound. So one sound occurs if you hit the billboard, and the other sound is played if you don't hit the billboard. When you build and run this, you may end up with an error, and the error may look like this. It says the program can't start because fmod DLL is missing from your computer. Try reinstalling. And what this means is that it can't find that fmod DLL. So in order to run these fmod functions, it has to be able to load that fmod DLL. And again, mine is located, when I installed it, it got located in this program files x86 fmod API low level library file, and here's the fmod DLL. So we either need to take this DLL and copy it somewhere where the executable can see it, so maybe into the project folder or the debug folder, or Visual Studio has the capability of expanding the environment path to include this folder. So if you take this and add it to this environment variable that's in the project properties debugging section, so you go to project properties, debugging, environment, and you say path equals, and then put in this entire path, then when you run the program through the debugger in Visual Studio, or if you run the program through Visual Studio, it will add that path to the executable environment, and the executable will be able to find that DLL. So if we go to the project properties, we will see that we've got this path added, and additionally we have added the path for the include folder for the fmod include file, and we've added the library folder for the fmod library file, and we have added the fmod library file to link against here. So a lot of this is similar to what you've done with DirectX and with the DirectX toolkit. We just have the additional step of adding a path to the folder that has the DLL that we need. And if for some reason we wanted to add another path for another folder that had other DLLs that we might need, we could just separate them with a semicolon. That's typical Windows path setup. Once you've done all this and we build and run it, we get our picking demo, and when we press something that doesn't hit, we get this typical Windows sound which tells us we didn't hit anything, like some error occurred. When we hit something that we're trying to hit, we get this chimes sound effect. So that's the basics of using fmod to initialize the sound system, load up sound files, and then play them. And if you had some background music and you wanted to play it with looping, you could set that up at the beginning as well. So I look forward to seeing what sounds end up in your project, and let me know if you have any questions.